Hello and welcome to this lecture about k-means. K-means is like the clustering algorithm, so whenever you think about clustering, k-means is usually the algorithm people think about. So today we were going to talk about this, and first let's have a little recap about what we did in the last lecture, because SVD and truncated SVD and the matrix factorization problem is actually quite related to k-means. So last lecture we have seen that truncated SVD solves the rank R matrix factorization problem. And yeah, what was the rank R matrix factorization problem? We had given a data matrix D and a rank, and then the task was to find the vector matrices X and Y of the lower rank whose product approximates the data matrix, and here we wanted to minimize this residual sum of squares. So we want to minimize the approximation error. And this solution was then given by the truncated SVD. So truncated SVD was that if we have the full SVD here, then we choose the vector matrices X and Y such that the approximating matrix Y times X transposed takes the truncation of this SVD. So we take here the first R columns of U and V, and also select from the diagonal matrix sigma here the top singular values. And then we had this scheme here, right? So we had here the data matrix, which is n times d. And this one was then approximated by this product of these three matrices, the diagonal matrix with the highest singular values on the diagonal, and the corresponding R singular vectors on the left and on the right. And we also have seen that SVD is actually a non-convex problem, although we can actually denote the solution by the help of SVD, so the global minimum. But nevertheless, it is a non-convex optimization problem. And as application for this problem, we have seen the recommender systems. So the example was a matrix where users can rate the movies they have seen, which are the rows here. Then the question was like, what could we also recommend to the users? And then we used here a quick hack to apply SVD as it is. And we replaced here all the missing ratings with the mean rating. So there we say we don't know to which tendency it goes, like does the user like it or not. We just stay in the middle, so to speak. And then we apply the SVD, and then maybe we give an insight into if the user would like the movie or not. And the interpretation of this factorization was then here given, for example, for the first row. We take here the first row times the second matrix, right? And then we have here the factor minus 0.3 for the first pattern. So this is here one pattern of movies, and here this is another pattern of movies. And then we had here these coefficients 0.3 and 0.5, to which this user can be assigned to the corresponding pattern. And yeah, one of the problems here was due to the negative results. And also you see here that the ratings are outside of the range of the actual ratings, right? So we have your ratings between 0 and 5. But here we get a value of -9. So maybe we can normalize this and then multiply this with a factor such that the coefficient here on the left would be then higher and everything on the right would be between 0 and 5 or something like that. But yeah, then we have to post-process our result in order to get more interpretable results. And yeah, at times this can be undesirable, right? So if we post-process things and we always introduce some assumptions about our data, and maybe it's just more desirable to directly get a model which has interpretable properties. And in one sense, k-means can deliver that. But first of all, let's start at the beginning. So first, let's have a look at the informal problem description. So what kind of problem are we discussing today? The example I chose for today was the clustering of cards. So if you think of a stack of cards, how do you cluster them? And clustering means to group data points according to a similarity criterion. So what are similar cards? Like how would you separate or distinguish groups of cards in a deck of cards. So one possibility would, for example, to cluster by color. Then we have one cluster of the black cards and one cluster of the red cards. But we could also cluster by number. Then we have many more clusters. So depending on how you treat then these symbolic cards, you have either 11 clusters or 13. So then all the numbers are one cluster, and Jack, Queen, and King are also one cluster. Or what you could also do is cluster them by their symbols. So is it hearts or clubs or spades or diamonds? All these clusters are somewhat justified, right? There is not one way to say, okay, this clustering is definitely more plausible than the other. And depending on the definition of the cluster, so for example, is it by color or by the numbers, then you also see that you get other numbers of clusters. So you get completely different partitions. And yeah, this is a very inherent problem in the task of clustering, that there is usually not one solution, but that it is more about exploring the space and then having some assumptions about what we're looking for, and then trying to get a clustering which actually matches our expectations the most, or which answers a question we have been formalizing over the data. So clustering is a task with multiple valued outcomes. Here, for example, you see the plot of 3 clusters, so then you have here these 3 blobs, right? But yeah, there could maybe also made an argument that these 2 clusters are maybe belonging to the one cluster. This is a bit unclear, but usually I would say that these are 3 clusters. And for clustering, these 3 questions which are outlined here matter. And the questions are, how many clusters do we have? Like if we say we have 2 clusters, then we would have the outcome which is in green, so then we would maybe make it these 2 clusters. But if you say it's 3, then it would be the purple one, right? Then the question is also, do they overlap? For example, this point here, does it belong to the left cluster or to the right cluster? It's quite in the middle, right? Can it maybe belong to both? That is a question which changes a lot the clustering we get in the end. And the last question is, how are clusters characterized? So this aims here at the objective function, which we are going to minimize. Yeah, and then depending on how you answer these questions, you get different clusters. So when we answer these questions, then we can actually develop there with a formal problem definition. So for k-means, we have the following answers. How many clusters do we have? Well, we just let the user decide. So the number of clusters will be an input to the method. And the question, do they overlap, is answered with no. Every point belongs to exactly one cluster. And that means if we have here these clusters, so these are sets of points, they have no overlap, so the intersection of them is the empty set. And the union of all clusters returns the set of all points, here indicated by their indices. And then we have a partition, so every point belongs to exactly one cluster. And the set of all partitions from these n data points we have is then denoted with Pn. And the last question, how are clusters characterized? So the answer for k-means is here that points within a cluster are close in average. And then we have here this formula. And this formula returns the average distance of 2 points in a cluster. So this here is the sum over all points in one cluster, and we sum here the distance of these 2 points in one cluster, and then we normalize with the number of points in one cluster. That means if you have here one cluster consisting of these points, then the value which is given by this formula here for this particular cluster with the points combines the lengths of the distances between every point. So you have here basically a fully connected graph. Okay, I hope I got now every edge. And then what this term here is returning is the average length of these connecting lines here, right? So it could be, for example, something like this. So here we have smaller edges, and we have also longer edges, but this could then be the average length of these edges. Okay, so points within a cluster are close on average, makes sense. Therewith, we can now formulate the k-means objective. So we have now given our data matrix D with n observations for D features. And we get also, as we discussed, the number of clusters as an input. So this is here R. And the task is then to find cluster C1 until CR, which formulate a partition of all the data points and which also minimize the distance between points within clusters. And this is then also called the within cluster scatter. So the objective here is to minimize over all these partitions here the distance function, and the distance function is given here. So this part is what we had before. So this is the average distance of points within one cluster, and here we sum now over all clusters. Okay, so this is the k-means objective. Now the question is, how can we optimize this? And we have here now a problem. And that is that the standard optimization methods which we have used so far in this lecture do not apply. We cannot use them because we have here a discrete optimization problem. We're minimizing over a partition here. So we want to find the best partition, and we cannot compute the gradient of a partition. So how can we optimize the objective of k-means when the gradients are not defined? So what we do now is transform the objective to get a better idea how to approach this problem. Yeah, and what we do here now is to swing our magic math wand, and then we get that minimizing the within cluster distance is equivalent to minimizing the distance of points to their centroid. So here, by this transformation, we get the notion of centroids. And if you want to know how that transformation goes, then you can have a look in the math PDF. So the result here is that the k-means objective, which we have defined before, is equivalent to this objective here. And like in the previous definition of the objective, we minimize here over all clusters, which create a partition of the data set. Here we sum over all clusters, so S is an index of a cluster, and then for every cluster we sum the distance of a point to its centroid. And XS, the centroid, is defined as the arithmetic mean position of all points. So we sum over all points in one cluster and divide it by the number of points in the cluster. Okay, does this notion of centroids now deliver more easily solvable subproblems? Maybe it's more easy to compute the centroids given the clusters and vice versa instead of computing clusters and centroids simultaneously. So the centroids are defined in our objective, right? We know how to calculate them, and we want to minimize the distance of points to their centroid. That also does not seem like a very difficult task. Okay, so let's go through an example. So the objective here is to minimize the distance of points to their centroids. And now let's just assume that we have some randomly sampled centroids. So these are here the purple diamonds. And the question is now, how do we assign points to clusters? So if we want to minimize the distance of points to their centroids, how would we assign now points to clusters? Well, the solution, you probably have guessed, is that we assign every point to the cluster with the closest centroid. So if we want to minimize the distance of points to their centroids, then we should always just assign the point which is closest to the corresponding centroid to this cluster, right? So then we get here this separation of clusters. So we have here now green, blue and red clusters, and then you see that we have here some decision boundaries. So for example, here the decision boundary between the red and the blue cluster is about here, and here we have the decision boundary between the green and the blue cluster. So the points which are blue are all assigned here to the middle centroid, and the points in red are closest to this centroid, and the green ones are closest to the left centroid. Now the thing is that these centroids, so the purple diamonds, are actually not centroids of the points in one cluster, right? So what should we do? Well, we compute them, right? So we compute now the centroids of all the points which are green, and of all the points which are blue, and of all the points which are red. And now we could again decrease the objective function by assigning the points to the closest centroid, right? So there we are now again at the beginning. And this is how we go on and go on and go on. So we solve these subproblems of assigning the points to their closest centroids, and then we computing the centroids, and then we repeat this procedure again and again and again. So this is now the k-means algorithm, and congratulations, you just came up with it on your own. I'm very confident that you did it. And yeah, this is the clustering algorithm, so not bad. Yeah, let's have a look just how that would like in pseudocode. So we have here the function of k-means, and this is actually known as then Lloyd's algorithm. And you see here it gets as input the rank, so the number of clusters and the data matrix. And then we have to initialize somehow our centroids. And then we compute the procedure as we have discussed it now. So as long as we did not converge to a solution, we do here these cluster assignment updates. So this is this step here. In this step, we assign the clusters to their closest centroid, and then we recompute the centroids. This is then the second step. So you see here in the first step that cluster with index S is the points for which centroid XS is closest. Yeah, and then we return what we got, so the clusters we received by this procedure. Okay, cool. We have now a algorithm, so we have now derived one possible method to solve this discrete optimization problem of k-means. But how good is it? Can we say something about its conversions? Is it like just a heuristic? So we thought, okay, this makes somehow sense that we now update the clusters and then we update the centroids and so on and so on. But can we really derive some quality guarantees of the result therewith? Well, all these questions can we answer under the more general framework of matrix factorization. And this is where we now go back to SVD and the rank R matrix factorization problem. But this we will do in the upcoming part of this lecture. So